Hi friends, Dr. Borole is here. Today we are learning common collector configuration. It is also called as emitter follower. Here the common collector configuration biasing for NPN transistor is shown in figure 1, and in figure 2 the biasing for PNP is shown. Here input junction is base to collector junction. The input supply is VBB. The input current is IB. The collector side circuit emitter to collector is the reverse bias circuit. The output current is the emitter current, and the VCC keeps emitter to collector junction in reverse bias. Since collector is common in between input circuit and output circuit, it is called common collector configuration. The current gain of the common collector configuration. It is denoted by the symbol gamma or gamma DC, and it is defined as the ratio of output current to input current. In this case, the output current is emitter current and input current is the base current. Since IB is much greater than IE is much greater than IB, and therefore this ratio is always greater than 1. Let us estimate the relationship between the current gain of common base configuration, that is alpha DC, and the current gain of common emitter configuration beta DC with the current gain of common collector configuration. We have the universal relationship IE is equal to IC plus IB, and that is nothing but beta DC into IB plus IB. That is equal to 1 plus beta DC into IB. Therefore, gamma is equal to, taking IB on left hand side, we are getting IE by IB is therefore 1 plus beta to DC. But we have derived already beta DC, that is equal to alpha DC upon 1 minus alpha DC. Therefore, gamma is coming out to be 1 plus beta, that is 1 plus beta DC, that is equal to 1 upon 1 minus alpha DC. The input and output resistance of the common collector configuration. In common collector configuration, the input resistance or impedance is very high because input junction is base to collector junction, and in linear region or active region, base to collector junction is always in reverse bias, and reverse bias junction have very high resistance. The output impedance is low because collector to emitter or collector to base junction, that is in forward bias in the linear region, and therefore the resistance of the forward bias region is low. The features of common collector configurations are tabulated here. The common terminal we found is collector. Input current is IB, output current is IE, the input voltage is VBC, the output voltage is VCE. The current gain is denoted by gamma, and which is high. The voltage gain is less than 1. The input resistance is high in this case, and the output resistance is low. Application of common collector configuration normally finds in the area of impedance matching or buffering. The comparison of various configurations are shown. Whatever we have derived for common base, common emitter and common collector, the same parameters are tabulated here. The common terminal, input current, output current, current gain, and so on. And that is your comparison table. The next concept is concept of load line. and the quiescent operating point. The first figure here shows the common emitter amplifier. The output circuit of common emitter amplifier is deduced from this circuit. If the base circuit is kept open, what is remaining is the output circuit shown in figure 2. The input circuit is derived from the again common emitter amplifier circuit by keeping the output circuit open circuited, and therefore you will see here the input circuit consists of VBB, RB and base to emitter junction. Combining circuit 2 and circuit 3 becomes a CE amplifier. Now, if you apply KVL to the output circuit, what is KVL? KVL is Kirchhoff's voltage law. So we see here VCC minus ICRC minus VC equal to 0. So see the output circuit. This is VCC. The voltage drop across RC is IC into RC with right side positive, left side negative. VCE top end positive, bottom end negative, and therefore it is opposing to VCC, and therefore VCC minus ICRC minus VC equal to 0. Take VC on left hand side. So it becomes VC is therefore VCC minus ICRC. Now take IC on left hand side and other parameters on right hand side. So you got the equation for IC, that is VCC by RC minus 1 by RC into VCC. So you will see that if you plot the characteristic IC versus VC, that is nothing but output characteristic. So this VC is nothing but x-axis variable and IC is nothing but y-axis variable. And therefore this IC equation is analogous to y is equal to mx plus c, where c is the y-axis intercept, that is VCC by RC, and m is equal to 1 by RC. So therefore same thing is shown here. There is a line drawn. The y-axis intercept is VCC by RC here, that is IC equal to IC max. When we substitute VC equal to 0 in this equation of VCE, see here, when VC equal to 0, ICRC becomes equal to VCC, and therefore IC becomes maximum, that is VCC by RC. Similarly, on x-axis crossover point of this line, this point B, the y variable is 0, that is IC equal to 0. So substitute IC 0 in this equation of VCE. When IC is 0, ICRC will be 0, and therefore VCE becomes equal to VCC, and therefore we got the second point. Point A and point B we have joined on the characteristic, output characteristic or VC versus IC characteristic of the device. It crosses the base characteristic, say IB equal to IB2 at a point. We can denote this point as Q point. Let us say IB2 is nothing but IBQ set by the biasing circuit. The corresponding value of IC is denoted by ICQ, and the corresponding X value or VC value is denoted by VCEQ. The regions are marked here. The region very close to x-axis for the curve IB less than IB equal to 0 or below IB equal to 0 and x-axis, that is cutoff region, where IB0 gives rise to IC0. So therefore device is off. The region near y-axis where VC equal to 0 and collector current is maximum. Therefore device is in saturation, and therefore this region near y-axis is called saturation region. Whereas the remaining region where this horizontal portion of the characteristics are shown, this is called active region. The operating point when moves in this active region portion from this crossover point shown here and this crossover point IB equal to 0 in the figure, that operating point motion will be in active region. Whenever operating point goes in cutoff region, the device will be off, and whenever operating point goes in the saturation region, device is fully on. In between the active region points, the device works as amplifier. The line drawn on this characteristic, say line AB, is called as load line, and that is the impression of this equation IC is equal to VCC by RC minus 1 by RC into VCC, and this is called as load line. Similar load line can be drawn on base circuit also. If you see the base circuit, we can write the equation VBB minus IBRB minus this VB equal to 0. Same thing is written here, and therefore IB is equal to VB by RB minus 1 by RB into VBE. Is similar to again Y equal to MX plus C. So it traces the line on the input characteristic here based to emitter characteristic VBE versus IB, on which this equation traces a line, whereas y-axis intercept is VBB by RB and x-axis intercept is VBB here. Now if you see here, if VBE changes, the operating point is moving, and if operating point is moving from this Q point to Q1 and from Q1 to Q2, the IB is changing from IBQ to IB2 and then to IB1, again IBQ. Therefore, if input VB changes by the triangular wave shape, then base current is also changing and following the triangular wave shape. The next topic is biasing circuit. Now we have seen up till now the biasing of the transistor can be done in various region or in active region by using batteries. We use VBB and VCC, two power supplies, whereas it is very inconvenient in practical circuit to have multiple power supplies. And therefore, the biasing can be done with single power supply with a combination of resistances forming a voltage divider, and that deduced voltage can be used for biasing the input circuit and output circuit. Accordingly, there are three types of biasing circuit evolved. Fixed bias circuit, also called as single base resistance biasing, collector to base bias circuit, and voltage divider bias or self bias. Whereas voltage divider bias or self bias is most commonly used in practice to bias the transistor in linear region. Therefore, let us see the voltage divider bias or self bias. So here the VBB, base to emitter circuit power supply VBB, can be achieved by using a voltage divider formed by the two resistances R1 and R2, and it is connected across the supply voltage VCC and this ground terminal. Therefore, when the resistances are connected across the supply, they divides the voltage. Current is flowing through these resistances. So total current flowing through the resistance R1 and R2 is VCC divided by R1 plus R2. Now when same current is flowing through R2 creates the voltage drop across R2, and therefore I into R2 is equal to VR2, and therefore it is nothing but voltage at point B, that is across R2, is nothing but R2 upon R1 plus R2 into VCC. This can be analyzed by using Thevenin's equivalent circuit. So here, to get the Thevenin's equivalent circuit, we will disconnect the base circuit first and look inside the resistance network R1 and R2. So we will see the open circuit voltage here at the base is nothing but voltage across R2. That is denoted as Thevenin's voltage VTH, and voltage across R2 from the voltage divider theorem here is R2 upon R1 plus R2 into VCC. Whereas if you look inside and find the equivalent resistance, then the resistance comes out to be R1 parallel to R2. And R1 parallel to R2 is nothing but R1 into R2 upon R1 plus R2. And therefore, the equivalent circuit, Thevenin's equivalent circuit consists of a battery source VTH in series with the resistance RB, that is R1 parallel to R2. And remaining circuit part is same, that is transistor RC and RE. So this is the equivalent circuit, Thevenin's equivalent circuit of this complete transistor amplifier circuit. This is normally used for analyzing purpose. Now we can estimate the Q point from this Thevenin's equivalent circuit. The Q point is nothing but the value of VCQ and ICQ in the output circuit and VBEQ and IBQ in the input circuit. Now here the input circuit is redrawn. By observing this, you will see the input circuit is this circuit shown here is copied as a figure here. Now we can see we have already VTH is equal to R2 upon R1 plus R2 into VCC and RB is R1 parallel to R2. Now, if we want to find out the expression for base current, we apply the Kirchhoff's law here. Now apply it. Total supply voltage VTH is equal to IBRB plus VB plus IERE, or you can say VTH minus IBRB minus VB minus IERE equal to 0. Taking all the negative terms on right hand side and IB on left hand side, and also substituting the value of IE in the equation. IE we know equal to beta into 1 plus beta into IB, and then take the IB common from this equation. So therefore IB comes out to be VTH minus VBE divided by the resistance RB plus in bracket 1 plus beta DC into RE. So we got the base current value from the input circuit. Now if you want to find out the expression for IC, let us consider the output circuit. We know the output current IC is nothing but IC equal to beta into IB. Just substitute the value of IB we have derived. We get the expression for IC. If we want to find out the expression for VCE, apply the Kirchhoff loop equation. So we got by using KVL to collector circuit VCC minus ICRC minus VCE minus IERE equal to 0. Taking VCE on left hand side, VCE is equal to VCC minus ICRC minus IE into RE. Now let us study transistor as amplifier. Now in the circuit, the basic block diagram of voltage amplifier is shown. The input is applied to the voltage amplifier. Here Vs and Rs constitute a source. Rs is the source resistance. Input to the amplifier is Vi. Input current to the amplifier is denoted by II. The impedance looking or resistance looking inside the input terminal is called as input resistance. If you see the output circuit, the load resistance is connected across the output terminal and the output current is flowing through this load resistance develops the output voltage. The additional DC supply is provided here, that is VDC, normally called VCC, that is supplying the energy for amplification. Normally input voltage is small, that gives rise to the input current II. This II will be amplified by the amplified device, normally BJT, and amplified version of the current available as IO. So in BJT case, this II is IB and IO is IC. And we know IC and IB are related by the factor beta, and therefore Output current is the amplified version of the input current, and therefore the output current when close to the load resistance develop the large output voltage. So from small input voltage Vs, we will get the amplified output voltage, and thus the transistor acts as an amplifier, voltage amplifier. The various characteristics of the amplifier are listed here. First characteristic is the voltage gain, that is denoted by the symbol AV, that is nothing but VO by VI. The current gain, that is denoted as AI, that is nothing but IO by II. The input impedance, denoted by the symbol RI, and that is the ratio of input voltage to input current. The output impedance RO, that is the ratio of output voltage to output current when input voltage is 0. The fifth parameter is bandwidth, and that is the difference between the upper cutoff frequency and lower cutoff frequency, FH minus FL. How BJT can act as a current amplifier, that we will see. Now BJT, the input current, see the circuit here in common emitter configuration. The input current is IB and the output current is IC. And we know IC is much greater than IB by the factor beta. Here, if input voltage is applied, which cause the base current to flow, this base current causes the large beta times large collector current to flow in the collector circuit. So obviously, if we see the collector current as output current and base current as the input current, then IC is the amplified version of IB. The same thing is represented here graphically. Let us see the output characteristic curve. Here, three characteristics are shown: IB1, IBQ, and IB2. Let us say IBQ is 80. The load line is drawn here. The load line intersects with IBQ. That point is Q point. Now, if input voltage Vi changes, according to the input circuit equation we have seen earlier, IB changes due to change in Vi. If Vi increases, IB is changed from IBQ to IB1. If Vi decreases, IB is changed from IBQ to IB2. While changing, let us suppose that input is changing sinusoidally, therefore IB is also changes sinusoidally. If you project all the points of this sinusoidal lines on this load line and find out the y-axis points, IC is changing from ICQ to IC1, then coming back to ICQ, then coming to IC2 or IB2 value of input, and then again ICQ for the complete cycle. And therefore, if input changes, base current changes sinusoidally, the collector current changes sinusoidally. The collector current is beta times higher than base current. And therefore, a typical value here shown, if beta is 100, the probably 80 microampere quiescent current gives here the quiescent current of 8 milliampere. If IB changes from 80 microampere to 100 microampere, the collector current changes to 10 milliampere. If IB changes to 60 microampere, the IC changes to 6 milliampere. The corresponding value of VCE is shown here. When the Q point is moving from this Q to Q1 here and Q2 on the downside, VCE changing from VCQ to VC1 and again back to VCEQ and back to VC2 and back to VCEQ again. So for entire cycle of the input current IB, there is an entire cycle of collector current and there is an entire cycle for the VCE value. But one thing to be noted, IB and IC are in phase, whereas the waveform of VC is 180 degree out of phase shifted with IB, and which is also therefore VC is 180 degree phase shifted with VI, and therefore common collector configuration provides 180-degree phase shift. So what we have seen in CE configuration, the output current is IC, input current is IB, therefore current gain is IC by IB is equal to beta. Whereas in common collector configuration, output current is IE, input current is IB, and therefore current gain AI is IE by IB, that is 1 plus beta. Now let us study transistor as voltage amplifier. The circuit is same. We have seen IC is the amplified version of IB. The simple reason, if we take the output as instead of current, if you take output as a voltage here, since the name is a voltage amplifier, so output VO is shown here as VCE. The operation here is shown by this equation. VO is equal to VCE is equal to, we have a equation VCC minus ICRC, that is nothing but VO. This is a Kirchhoff loop equation we have already applied earlier also. Now during the positive half cycle here of the input, if input is increasing, base current is increasing. If base current is increasing, the collector current is increasing. And according to the voltage equation here, VO equation, VC is decreasing because IC is increasing. So VCC minus ICRC is decreasing. During negative half cycle, here there is a misprint. Consider this as a negative half. During negative half cycle of the input, the input is decreasing. That gives rise to IB decreasing. If IB is decreasing, IC is decreasing. And if IC is decreasing, according to the equation of VC, VC is increasing. Therefore, if input is increasing, VC is decreasing. If input is decreasing, output is VC is increasing. So there is 180-degree phase shifted relationship. Since IC is much greater than IB, that is beta into IB, therefore VC is large. When this large IC is flowing through the resistance RL or RC, then it produces the large voltage drop, and that's why small change in VI gives rise to small change in IB, gives rise to large change in IC, and large change in IC produces the large voltage drop across RL, and that is nothing but the output voltage VO, and therefore larger output voltage is generated from smaller change in input voltage, and that is nothing but the amplification, and the ratio of output voltage divided by input voltage is called voltage gain. So we have just written the equation. If you apply the KVL to base circuit, see here VI minus IBRB minus VB equal to 0. Concentrate on this VI, this is IBRB minus this VB equal to 0. Take IB on left hand side. So VI minus VB by RB equal to IB. If we consider the deviation, here VB is constant, and therefore delta IB comes out to be VI by RB because VB is not changing. So VI is changing, therefore VI by RB is equal to IB. If you apply KVL to collector circuit, we can say VO is equal to VC is equal to VCC minus ICRC. This equation is repeated now more number of times. So I think you are understanding the equation by heart now. So if you see, take the change in VO, here VCC is a constant DC supply, and therefore if you take the deviation, delta VO equal to delta VC is equal to, that is nothing but IC into RC. So therefore IC is a changing part, therefore we are saying delta IC into RC. So therefore delta VO is, substitute IC value here, that is beta into delta IB, and substitute the value of delta IB, that is VI by RB. Therefore voltage gain is defined as delta VO by delta VI. Take delta VI on left hand side from this equation. That is nothing but beta into RC by RB. Since in this equation beta is multiplied by the ratio of RC by RB, the voltage gain of this circuit is therefore large because beta is large. If we select larger value of RC than RB, then voltage gain will be further larger. So this equation tells us how exactly the voltage gain is achieved. Whereas logically we have seen from the operation here that output voltage is larger than input voltage. But this voltage gain equations actually tells us how much larger the output voltage is from the input voltage. The graphical interpretation of the operation, now we will see whatever we have discussed logically, same can be represented graphically also. Let us again draw the output characteristics. Here it is a Q point. Now we will see load line is drawn. If IB is changing sinusoidally, IC is changing sinusoidally. We have seen this curve already. So here when IC is changing sinusoidally from 8 milliampere to 10 milliampere, VC is changing from VCEQ to this value. And this VCE equation is nothing but VCE is equal to VCC minus IC RC. So when IB changes from the quiescent value IBQ to IB1, IC changing, the operating point is moving on this load line up and collector current is changing to IC1 from ICQ. When input current IB is decreased from IBQ to IB2, the quiescent point is moving on this load line on downside, and therefore IC is changing from ICQ2 to IC2. In between points, if input is changing, base current is changing sinusoidally, the collector current also follows the same shape, and the equation for VCE traces 180 degree phase shifted VCE curve. One thing to be noted that these quantities, base current and collector current and VC, are riding over the DC value. See here, IC is riding over ICQ and VC is riding over VCEQ. The VCQ and ICQ are the DC values, whereas changing values are the AC values. If you want larger gain, then similar amplifiers can be connected in cascade. Or output of one circuit is connected to the input of the similar next stage, and the device which couples the output of the first stage, for example this VC, that can be connected to the next stage input, then the capacitor C2 can be connected and this VO can be connected as input to the next similar stage. Therefore, C2 is also called as coupling capacitor, whereas external source can be connected to the input via another capacitor called C1, that is also coupling capacitor. And main function of coupling capacitor is to block the DC voltage, because capacitor provides infinite or very high impedance to DC. So it acts as open circuit for DC. Whereas here the capacitance CE is connected across RE. This capacitor is also called as bypass capacitor because at high frequency this capacitor acts as a short circuit and bypasses the resistance RE. Let us list the important features of CE amplifier we have seen. Input signal is applied at base and output is obtained at collector. Voltage gain of CE configuration is high. Current gain of CE configuration AI is high, that is beta. Input impedance of CE configuration is Ri. Output impedance RO is moderate, and it provides always 180 degree phase shift between input and output signal. That's all, friends. In the next part of this series of lectures, we will see the another application of BJT, as a switch or transistor as a switch. Up till now, we have seen the linear application of BJT as an amplifier. So that's all. Bye bye.